Hi everyone, I am Tanumoy. I am a physics faculty at Cheenta. Today we are going to study a problem on a motion in a vertical circle. So this problem is very important for understanding of all the concepts that are going to be coming in Olympiads and several other competitive exams. So we are now going to see that how does we move something in a vertical circle, and how does, with the effect of its mass and gravity, we are going to give it a different speeds so that we can move it from the lower point to the highest point. So what would be the minimum speed that will be required to move a circle in a full path so that we can get its value in terms of G and R. So let's check it. So as we can see that we have a setup where we can actually make this pendulum move and its gravity is on and there is no air resistance, so that it only move in the effect of gravity. So when we try to move this with a certain velocity, let's give it a velocity in x direction and let's start. So we can see that it's reached its maximum point and coming back and forth like it's doing a simple harmonic motion. Okay, so now what we have to do to move it in a full circle? So let's increase the speed. So when you are increasing its speed, you can see that it's reaching to a higher point than the previous one, and due to which we can actually measure that how much depend on the radius and the gravity, we can see that how much actually the velocity would be required, and we are now going to calculate it. So how much is required for the motion in a full circle? So we have to increase the speed, right? So let's increase its speed to maximum as we can imagine. So yeah, at certain speed it is going to get a full circle, but how much is this speed? We need to calculate its value. So let's check it. So now we are going to calculate the motion in a vertical circle formula, that how much the velocity is at the highest point and how much it is required at the lowest point. So for the highest point we can take the velocity as Vh. We can take the tension at the highest point as 0 because there is nothing acting at the highest point. So tension at the lowest point would be maximum at its mg force that is acting at the lowest point. So now let's calibrate. So we can see that at some point t, it's making an angle theta with respect to the center. All right. Then we can calibrate its mass. Mass is always attracted towards Earth. So we can see that mg force will be acting downward. Okay, so with respect to this vector and this plane, if we take this plane as x and this as y, so we can see that, so this is mg cos theta and this is mg sin theta. So we have the vector components in the horizontal and the vertical direction. So if we calibrate in the x direction, we can see that tension force is just opposite to the mg cos theta component. So we can see that T minus mg cos theta is the net inward force, and this which is providing the necessary inward force is nothing but the centripetal force due to the tension in the string, that is mv square by the radius r. So we can write this equation as T minus mg cos theta is equal to mv square by r. So this velocity we will be requiring for highest point. So the net equation we can transfer is T is equal to mv square by r plus mg cos theta. When we see that there is a highest point, so what would be the angle at the highest point if you make a circle? So we can see that the angle it is making with the highest point is theta is equal to 180 degree. So we can see that cos theta is nothing but 180 degree. So cos of 180 degree would be minus 1. So we can substitute in this part and we can write that T mv T mvh square by r equal to plus minus mg equal to, this entire equation would be minus 1. So this would be the equation for calculating tension at the highest point. But we know that the tension at the highest point would be equal to 0. So we can say that mvh square by r is equal to mg, and this calibrates to the equation as vh square equal to gr. So we can say that the velocity at the highest point vh is equal to root gr. So this is the minimum velocity would be required at the highest point. Now we can calculate that how much is the velocity that will be required at the lowest point to move it in a vertical circle. So that we can do it with the help of conservation of energy. So with the help of conservation of energy principle, we can say that the net kinetic energy at the lowest point, because at the lowest point there would be no potential energy because the radius is like the height is 0 here, and it will be equal to the total potential energy at the highest point plus kinetic energy at the highest point. So we can calibrate this as half of m v velocity at lowest point square is equal to mass times gravity times, then the radius of the circle will be 2r in terms of r plus half of m vh square. So we have calibrated for vh the value of vh square, which is nothing but vh is equal to root gr. So we will now put in the equations and we will find out the velocities. So half of m vl square is equal to 2 mgr plus half of m gr. If we calculate this would come out to be 4 mgr plus mgr divided by 2, which is equal to half of mass times the velocity at the lowest point square. So this is how we can calculate. We can take the mass, we can cancel the mass from the entire equations, and we can write it as VL square is nothing but 5gr. So VL is equal to under root of 5gr. So this is the minimum velocity that would be required at the lowest point to move it, to reach it at the top. So now if we have taken, for example, we can take r as an experiment we are going to see as 1.5 meters, and g as usual we can have 9.8 meters per second square. So we can now calculate that how much would be the velocity at the lowest point so that it can reach the top. So VL is nothing but under root of 5 into 9.8 into 1.5. So if you calculate this will come out to be under root of 73.8, which is going to be 8.5 meters per second. So the velocity at the lowest point, the minimum velocity that you will be required is 8.5 meters per second to move it in a vertical circle. Now let's check this experiment in our algorithm, the virtual platform, where we will be calibrating our theoretical calculation with our practical application. So this is the experiment part that we have learned. Now we are going to calculate to the exact measurement that how much velocity should be required in terms of the v velocity at the lowest point that we have calculated is root 5 gr, so that we can reach to the highest point possible. So as you can see that this scale, it is almost 1.5 meters. So we can say that the radius of the circle that is going to be would be 1.5 meter, and we have the massless string and we have this bob. So the value we get by calculation of the velocity at the lowest point, that is minimum to require the bob in the full circle, is root 5 gr. So if we calculate root 5 multiplied by 1.5 multiplied by the radius of the circle and the if we calculate 5 multiplied by 9.8, that is the acceleration due to gravity, and 1.5 meter, that is the radius of the circle. So what we are going to get the value? We are going to get the value as nearest to 8.5 as we have seen. So let's now see what is the limit it reached at 3 meters per second velocity. So see, slowly we have seen that it is to a certain extent and not moving a full circle. Okay, so now let's give it a bit higher speed, and slowly we are going to calibrate that whatever we have theorized is according to our value or not. So let's give it a 5 meters per second. Okay, so when we give a 5 meters per second, see it reaches a little bit higher than the previous one. Okay, now let's increase the velocity slowly, and let's give it a velocity near to that we have calculated, almost 6 to 7 meters per second. So it gets some momentum, but it falls back because at the end of the string, the tension is almost zero at the highest point, so it is not getting enough velocity to overcome this effect. So let's increase the velocity further. I can see. Okay, so almost, let's say, what about 8? So our goal is to reach the highest point. So almost we have reached, but it falls back at 8 meters per second. Okay, now let's increase to 8.5. Little bit more than 8.5, 8.6. Okay, so yeah, we kind of reached the highest point and almost able to trace the entire circle. So beyond less than 8.5 it won't work, so we have to give it a velocity more than 8.5, and then we can see that it almost travels a full circle, let's say at about 10 meters per second. See, now we can see that, yeah, the kinetic energy it has gained is converted into the potential energy as we have seen in the formula, and it is traversing the entire circle in a vertical loop. So the motion in circle is now complete. Thank you.